About 13 billion years ago, in the aftermath of the Big Bang, the earliest particles in the universe started to come together under the pressure of the immense gravity and heat that was forming at the center of newly formed stars. This was the birth of atomic nuclei in the universe. As more and more protons became fused together with neutrons in the hearts of giant stars, carbon was formed, then iron, and other heavy elements whose nuclei happened to be stable. Then, the stars would inevitably explode in a supernova, collapsing under their own mass, spreading these newly minted atoms across the universe, and ultimately, many of them landed here on Earth. And with just the right mix of atoms and just the right set of conditions, after a few billion years, you get us. Everything you've ever touched, everything you've ever tasted or smelled, everything you've ever seen or heard, they're all built from those same ancient atoms. Even the very memories and emotions that you have right now about all of those experiences are ultimately just the result of intermolecular interactions between atoms that just happen to be in your brain. An interconnected array that is unfathomably complex, but nevertheless built from the same fundamental ingredients as any other object in our universe, and yet responsible for the very consciousness that allows you to be watching this video right now. The Nobel Prize-winning physicist Richard Feynman once said that if we had to condense all of the scientific knowledge that the human race had ever gathered into a single sentence to pass on to the next generation, it would be, everything is made of atoms. An atom is an incredibly small piece of matter. Trying to find a particular atom on a whiteboard, for example, would be like trying to find that whiteboard somewhere, anywhere, on the surface of the entire Earth. The scale is amazing. So how were they discovered? Well, we don't see them, obviously. We make observations and infer their existence from those observations. In other words, there are some realities that we can observe in the world around us that are effectively explained if we assume the existence of atoms. This is the heart of the scientific method and will be a central theme in this course. It's all about evidence. Evidence we collect from observation. We must rely on our observations of the world around us, and then infer from what we observe how matter is constructed at that most fundamental level. Much of this class will be focused on showing you what information we get by observing the world around us. Water boils at 100 degrees. Gases can be compressed. Metals conduct electricity. These are all empirical facts that we can see for ourselves. The trick, though, is figuring out what these facts can tell us about the nature of matter itself. That's what we'll focus a lot of effort on in this course. I don't want you to just memorize a bunch of facts. I want you to be able to see the link between evidence from observations and the theories about matter we develop from those observations. So back to atoms. You probably know from high school that atoms are built from particles called neutrons, protons, and electrons. But how do we know that? The atomic theory of matter is built by so many scientific discoveries, but one of the most important was that of Ernest Rutherford. It was actually an undergraduate student, much like yourself, in Rutherford's lab who made one of the most intriguing observations about the atom. The experiment goes like this. What Rutherford did was take a thin, extremely thin sheet of gold foil, only several atoms thick, and bombarded that gold foil with something called alpha particles. So we don't need to concern ourselves too much about what alpha particles are, except that they're highly energetic particles, and you can think of them like tiny bullets being fired at this sheet of gold foil. And what Rutherford and his colleagues noticed was that the vast majority of these particles simply flew right through the foil, which at the time wasn't necessarily a big surprise. But what was really interesting to the team and what really led to the notion of the atomic nucleus was that every once in a while, very rarely, but reproducibly, a particle like this one that I'm circling right here would be what's called backscattered. So it would actually fly back toward the user. So let's watch this particle continue. See how it flies that way? So if you were to put a detector around the foil looking for where these alpha particles go, again, you would find the vast majority go straight through. But by virtue of the fact that any particles at all backscattered, I mean, that's analogous to, at the time, they would have thought of this as firing a literal bullet at a sheet of tissue paper and somehow having that bullet fly back to them. It was an incredible discovery. And really what it showed was that the vast majority of mass in matter itself had to be concentrated in tiny little places, which they called the nucleus. Because the only way that matter would be able to backscatter these alpha particles was that if the vast majority of mass was concentrated in a single place. If you were to spread out the mass of this gold over all of the area of the foil, it just wouldn't have had enough mass to backscatter those alpha particles. So this was ultimately what led to Rutherford's notion that matter, at least most of the mass of matter, had to be concentrated in tiny, tiny places within the substance. And those places had to be positively charged. So we knew that the protons had to be there because that was the charge required to have backscattered an alpha particle. We also knew that the neutrons had to be in the nucleus as well because we knew that the neutrons carried an awful lot of mass, and the vast majority of mass had to be concentrated in these tiny little places. We knew those little places were tiny because relatively few particles ever got backscattered, and we knew that they had to be very, very massive because backscattering wouldn't have occurred at all unless they were. So this is really how we started building up the fundamental notion that a nucleus really contained all of the positive charge, i.e. all of the protons, and most of mass, i.e. the neutrons as well, all bundled up into an incredibly tiny volume relative to matter itself. So most matter is virtually empty space, and it's the electrons that occupy that space. And you can actually measure literally how big those nuclei are by looking at this phenomenon of backscattering. And the way you do that is actually not so difficult. As these alpha particles are incident upon these nuclei, obviously most of them fly through. But the ratio of how many particles get backscattered versus how many particles fly through the substance is exactly equal to the ratio of the nuclear volume versus the rest of the empty space. So you can actually work out, by counting how many particles backscatter, you can work out how big these nuclei actually have to be. And that's critically important because if you stitch that information together with all kinds of other experimental evidence from people like Robert Millikan, who worked out fundamental charge on an electron, you ultimately arrive at a table like this. And so here we see all of that fundamental information collected into a single table. We can see the charge on each of those fundamental particles, the proton, neutron, and electron, and we can see their mass. Notice that the mass is much, much bigger for protons and neutrons. And notice that a neutron has no charge. These are those fundamental pieces of information that we put together after years of experimentation and evidence collected from how matter behaves. Now, these numbers, as you should expect, are incredibly small. So take a look at the mass of a proton, for example, 1.6 times 10 to the minus 24 grams. That number is so unfathomably small that it is virtually impossible to truly comprehend, to truly wrap your mind around how small that number is on the scale of how we live our everyday lives. So what we do is, to make those numbers just a bit more manageable, we scale them into a unit system called the atomic mass unit. Likewise, with the charge, these are again incredibly small charges, as we should expect because these particles are impossibly small. So instead of the typical units of charge, like coulombs, we rephrase these into what are called units of electronic charge, or E. Now, That's just taking that 1.602 times 10 to the minus 19 coulombs and phrasing that as 1. And so we can see that our protons and electrons are oppositely charged exactly, and the masses of protons and neutrons are relatively the same, whereas electrons are much, much smaller, about 2,000 times lighter. And so this constitutes really the structure of matter, where we have all of this mass concentrated in this tiny little positively charged space called the nucleus, and then we have this relatively light space of electrons surrounding the nucleus. You know, they say if you were to take a nucleus and envision it as, say, the size of a glass marble, and if you place that marble at the center field point of a giant football stadium, you know, one of these 60,000 people football stadiums, that would be roughly the space that the electrons would occupy in a typical atom relative to the size of that small glass marble, being the nucleus of that particular atom. So that's why we say that matter is mostly empty space. But keep an eye on these values, because we're going to want to talk about them in a little bit more detail. So now imagine that we wanted to build an atom, say. We know what the composition should be like. We need protons, neutrons, and electrons. And as we start placing these particles into our imagination of what an atom should be, we can notice that there are certain combinations that are stable, and then there are certain combinations that are not stable. And you would notice that, generally speaking, the numbers of protons and neutrons tend to be more stable when they're the same. So if we wanted to make, say, a lithium atom with 3 protons, adding a 4th neutron is maybe okay, but if we go ahead and try to add a 5th, this becomes a problem. And so when neutrons and protons tend to be out of whack, we tend to have unstable elements, and this is mostly where radioactivity comes from, because these nuclei will spontaneously decay. Now, using this information, we can begin to put together the periodic table. So for example, I can place 6 protons on my atom and discover that that corresponds to an atom of carbon. I could put 6 neutrons on that carbon atom and discover that it's stable. But I could also put 7 neutrons on that carbon atom and discover that it's stable. So this is information that we're going to want to collect and understand on a systematic level. All right, so with all of these seemingly infinite numbers of ways to build nuclei, whether they're stable or not, and continuously add different amounts of protons and neutrons, and of course we haven't even started talking about electrons yet, how is it that we make sense of all of this information in a clear and concise way? The answer is the periodic table of the elements. Right? So we probably knew this already. The periodic table of the elements is a clear and concise collection of all of this chemical information in ways that is relatively simple to understand. It is organized in terms of atomic number. So if we zoom in here and look at a typical entry on the periodic table, say carbon, for example, carbon is element number 6, and what that really means is that its atomic number is 6. And what that really means is that it has 6 protons. Recall when we were actually building carbon over here, if I drag out a proton, notice that the scenario with 6 protons is carbon. And that is by definition. So every element in the periodic table, every element in the universe has been named by humans relative to the number of protons they have. That is the system we use. So if you have more protons, you are a different element. So we call you nitrogen if you have 7 protons. And so atomic number and number of protons is exactly the same thing. We often give it the symbol Z. So I would say Z equals 7 for nitrogen. So if I add just another proton, I don't have a different version of nitrogen, I have oxygen. And so that is how the periodic table is established. Numbers of protons is equated to atomic number, which is equated to what element you have. Okay, so I know that the difference between boron and carbon is at least a proton. Now, where do neutrons come into play? Neutrons will be the focus of my next video, but neutrons are obviously something that can change. I can have different numbers of neutrons, some stable, some not, within a particular atom. So this would be a version of carbon where I've got 6 protons and 6 neutrons and everything seems fine, but if I take one away, not so good. If I add a new one, that one exists too. So how do I track that information on the periodic table? I don't directly, okay? More on that later. But ultimately, where that will bake in is when we talk about the atomic mass. And so the entries on a periodic table are the element symbol itself, the number of protons that defines its identity as that particular element, and then on the bottom, typically we would have the atomic mass. And so these atomic masses, as you can see on this periodic table, are in units called U here, but this is the same as atomic mass units, or AMU, that we saw on the previous slide. So carbon has a mass of 12.011 atomic mass units. Okay, and we know what an atomic mass unit is, sort of, based on the slide we saw in the past. So when we take these elements in different chemical contexts, yes, numbers of neutrons can change, and frankly, numbers of electrons can change too, that we haven't discussed so much up to this point. But numbers of protons really does define the identity of an atom. Okay? Now let's talk about electrons just briefly in terms of counting particles. As I add electrons to this fictional carbon atom, what I'm doing is I am surrounding this nucleus with electrons. This is the sort of simplistic model that we know about when we think about electrons going around a nucleus. We'll get into that in far more detail later. But the charge that would be on an atom helps me do the math to determine what number of electrons this atom has. Now remember, if I have a carbon atom, I definitely have 6 protons. That is the definition of a carbon atom. But if I have, say, carbon plus, so a carbon that is positively charged, then I must have 1 less electron than I had protons, which tells me by definition I must have 5 electrons. So carbon with a plus charge is guaranteed to have 5 electrons. Likewise, if I add a couple, and I know that I've got carbon minus, so if I have a carbon minus element or a carbon minus atom, I must, by definition, have 1 more electron than I have proton, because I know that electrons are negatively charged. Now, neutrons are something else that we'll have to keep track of. Notice in this particular case, I happen to have 1 more neutron than I have protons. So in this particular case, I've got 7 neutrons. But interestingly, when we add more neutrons to an element, it doesn't always behave chemically different. Okay, now the reason for that is because those neutrons are not charged, and most of chemical behavior is governed by charge. Positive charges being drawn toward other negative charges, and vice versa. So atoms that form bonds and break bonds and get drawn to other things, which we will talk about in depth over this semester, it's really mostly governed by charge and how charge is distributed through space. But because neutrons don't have any charge, they don't always impact chemical activity very much. All right. So, how do we determine this? Well, I'll talk about how we determine numbers of neutrons in my next video. But how we keep track of them in a sort of notational way is using something called the mass number. All right. So the mass number is a very simple sum of numbers of protons, which in this case is 6, and number of neutrons, which in this case is 7. So if I add 6 plus 7, I can see that my mass number for this particular element that I've built is 13. Now, why that's important is because it allows me to specify exactly the numbers of particles in my nucleus, right? There are 13. So I would use the phrase carbon 13 in this particular sense. So we can often talk about our element in terms of the particular mass number. So if I say carbon 13, because I've said the word carbon, you know that I definitely have 6 protons in the nucleus. That's what carbon means. If I say carbon 13, I can take that 6 away from 13 and I'm left with 7, and that guarantees me that I've got 7 neutrons in my nucleus. So in other words, the mass number, which we often give the symbol A, is equal to the number of protons, which we give the symbol Z, plus the number of neutrons. Okay, so you can do that math to figure out which element you've got. Now, if I take away a neutron from this example, we can see that I now have carbon-12. And when we talk about isotopes in the next class, I will talk about the fact that carbon-12 is actually the most abundant form of carbon in the universe, and certainly the most abundant form of carbon on Earth. Now, that happens to be because the combination of 6 protons and 6 neutrons in the nucleus is incredibly stable. That is the happy place for a carbon nucleus. And so therefore, it tends to be very common, and we have it a lot. Now, why I'm picking on carbon-12 in particular is because this is actually where the system of atomic mass units comes from. So we base the atomic mass unit system on carbon-12. In other words, what we say is that if we had a single element of carbon-12 and put it on a scale, we would define the mass of that carbon-12 atom as exactly 12 atomic mass units. Now, this is potentially an arbitrary choice. We could have chosen anything. But the thing to know is that unit systems are usually arbitrary. For example, I could define the distance between the UPEI campus and my house as exactly 1 Jason. That would be a silly thing to do, but it would be scientifically valid. That distance I could define and announce to the universe that that is a distance of 1 Jason. And then I could go on vacation and somebody could ask me, where are you going? And I could say, well, I don't know. I'm driving 5 Jasons away and I'll see where I get. Totally valid scientific statement. A little bit weird, a little bit esoteric, of course, but my point is that all unit systems are in some ways arbitrary. You have to make a choice about what to base that unit system on. And the atomic mass unit system, which we are using to describe all these particles, we're starting at the nucleus in this class, working our way out, and so we can ultimately talk about molecules and phases and all kinds of interesting chemistry. But the point is that we need some unit system to base our discussions on because these units of grams were, worked out to be impossibly small numbers. So we take the atomic mass unit, and to define it, we simply chose carbon-12, and we said arbitrarily a carbon-12 element weighs exactly, with infinite precision, 12 atomic mass units. So then all you do is you divide that number by 12 and you get the value of 1 atomic mass unit. And then you can go looking at all of the elements and all of the particles and say, well, how many atomic mass units do all of these weigh? And that's where we get the masses for all of these elements in terms of atomic mass units, which is essentially the universal unit system for talking about elements and really anything on the atomic scale. Turns out that 1 atomic mass unit happens to equal 1.661 times 10 to the minus 24 grams. So impossibly small number, but now that we're going to work with atomic mass units and we have something to base it on, which is carbon-12, we are able to express the masses of all of the elements in the periodic table. So, to summarize, now we know, based on fundamental experiments like those of Rutherford, that all of the mass and positive charge of an element has to be concentrated into this tiny little volume. We'll call that the nucleus. If we know that there are particles like electrons, protons, and neutrons, then because all the positive charge has to be in the nucleus, we know that's where the protons are. Because all of the mass has to be in the nucleus, we know that's where the neutrons are as well. And then we know that the electrons must be distributed elsewhere, and those electrons must be very, very light, and they must have a fundamental charge which can be measured, and we know that that charge has to be the same as protons because elements can be neutral, which means they would have the same number of electrons and protons. Now we keep track of all this information using something called the periodic table of the elements, which I'm assuming you're all familiar with, and we give a label to each and every combination of nuclei according to its number of protons. So if something has 34 protons, we call it selenium. And now you can play with the number of neutrons that are on there, but it's going to be called selenium. Now, if we want to call it something more specific, like, for example, selenium-68, well, that's great, but now we're being more specific and we're actually talking about how many neutrons are in that nucleus as well. And if we want to express it as a charged species, so for example, selenium plus, then we would know that if it's positively charged, there must be one less electron in that system, and therefore there must be 33 electrons in that selenium atom. Okay? So we're now able to figure out the numbers of all of these subatomic particles that must exist for any particular element. All right, that's a very valuable skill to be able to have. Okay, now this mass that's written on the bottom, this is the atomic mass of each of these elements, and it's expressed in atomic mass units. Now we have an idea about where the atomic mass unit comes from, but there are still some questions to resolve, I think. So for example, if carbon 12 is what we base our unit system on, why is this atomic mass not exactly 12? More on that later.